Okay, so good afternoon and thanks for staying, the brave ones. Okay, so I'll speak about a problem which is motivated by my work and other work that I've been doing in evolutionary biology. And you can find the details here. Okay, so as you know, that this very complex and diverse life that we see today on Earth is shaped because of the evolution that has happened during this last few billions of years. And this evolution, however, is a very complex process. There are various quote unquote forces at play. So for example, there are mutations. All of us heard about mutations during pandemic, for example. There's selection, which means certain mutants are better or worse than others. But actually, typically, mutants are neutral. That is, they don't change their fitness. So there are good mutants, bad mutants, and neutral mutations. Okay. Also, realistic populations are not well mixed, something which we do a lot in StatMech, but actual populations are specially structured. Then also there are the various different sources of noise, and that's why I'm interested in these kind of problems. So anyway, many of these forces are act simultaneously, and also these forces or the associated parameters are not constant in time. So it's a pretty complex problem if you want to model realistic situations. So what people tend to do in the subject is to say that, okay, we have tons of parameters, but we would like to reduce them to a few effective parameters and subsume the complexity due to others in those few effective parameters. So just to give you an example, suppose I have a large population of some bacteria or something, and a mutation occurs. And this mutation is very lethal, meaning it almost kills the bacteria. So I started with this much population, and the selection is acting strongly against it. So basically, because many of them will die, so I'm left with a smaller population, right? Because that will be propagated and contribute to evolution. So the effect of selection, therefore, can be subsumed in an effective population size, which is smaller than the actual census population size. So that's the basic idea. And what people do in the community is to take a complex model and then run the simulations, which has lots of parameters, and equate it to a simpler theory, which has effective parameters. Okay, so that's what people usually do. And of course, they do it because it works sometimes. Other times, this strategy doesn't work, and it's not very clear in what parameter regimes this would work. It's not obvious also what may be the reasons when it does not work. And finally, what may be the implications when it does not work. So these are the sort of broad questions that one is interested in. And I will just do a very simple model because I just wanted to understand what they are saying, basically. Okay, so the model that I have in mind is because most of you have not heard about this model, so let me introduce it to you. It's a very simple model. So it's after the Fisher, all of you know Fisher, and Wright was on the other side of the Atlantic, Sewell Wright. Okay, so this is after these two guys, Wright Fisher. So what I have here in this model are two types of particles, the dark blue and the light blue. The dark blue and light blue, they're equally fit. They're not better or worse than the other. It's just the color is different. So the dark blue is I'm going to call a mutant. So suppose I start with a population in which I have n-1 wild type and 1 mutant, and the dynamics are as follows. And the next generation, each of these individual, each offspring, it chooses its parent with equal probability. So for example, in this box, if I want to fill in which of these 5, it chooses a parent with probability 1/5. And similarly, this guy chose this guy to be a parent with probability 1/5. So that's it. So that's the sort of the simulation that you can run on your computer. Okay, so if I don't allow any mutation, that means dark blue and light blue cannot transmutate into each other, then you can convince yourself that if you run this program, and eventually you will have two absorbing states. All will be either dark blue or the light blue. Eventually one of them gets fixed. So when this happens, like all dark blue have become, we say the mutant has got fixed in the population. Okay, so you can write down a standard way of dealing with these things is to write down backward Fokker-Planck equation. And for the model I described to you, the Fokker-Planck equation looks like this. The second derivative with respect to the frequency. There's a p into 1 minus p term outside here, and the population size is over here. So this model can be solved exactly. This is known for a very, very long time. So there's this, a large time answer. But if you do an eigenfunction expansion, this is the eigenvalue part, and this is the eigenfunction which can be written in terms of hypergeometric functions. And because we know how to solve this problem exactly, all the standard, because we are dealing with the first absorbing state problems, all the standard first passage time problem, quantities that we're interested in, like fixation probability, time, sojourn time, etc., all this can be answered. Today, however, I'm interested in asking that suppose this population size is not constant in time, because that's a realistic situation. Population size is never constant. It always changes with time. Okay, so the model is that now population size is fluctuating in time. So if I had 3, 3, 3, and then suddenly it becomes 5 and 3 and so on. Okay, so that's the model here. So now in this case, the dynamics are as follows. So again, this if the population size, total population size changed, then this guy chose this to be a parent with probability 1/3, but you do the sampling 5 times. So that's the only difference in this model. Okay, and I have not specified to you what's the process of the total population size, but right now it's all general. Okay, so if you do that, then the corresponding Fokker-Plec equation looks like this. So I have the second derivative term, p into 1 minus p as before, but now this coefficient is time dependent. Typically what we're interested in is to average things over these trajectories of the population size, right? So which means when I did this my eigenfunction expansion, I need to do this averaging. That's what the angular brackets are denoting. I need to average it over these population trajectories. Okay, so let's look at it again. So, what it means is that you have to average it, the population trajectory is till time t and keep on averaging it. I find it easier, and I guess all of you also, to write this in terms of cumulants. So therefore, this average is equal to this infinite sum in the exponent. So it has terms like the average of the inverse population size, 2-point correlation function, and so on. Okay, so if population size was constant, then of course you have the simple answer e to the power minus t by n, right? Okay, but okay, so because all these terms will drop out and this integral is trivial. If population size is uncorrelated in time, that means I pick this new population size every time from randomly. In that case also, all these terms also again drop out and I'm left with just one term. So that's what these people in biology, they define as effective population size, inspired by the constant population size answer, saying that, this looks almost like that, but now I have effective population size, which is this. So that complexity due to the changing stochasticity is subsumed in a new population size, and it's as though it's some constant or something. And it's commonly used to analyze and interpret the data. Okay, so this is all fine, so long as population sizes are uncorrelated or constant in size. But this is again biologically unrealistic, so we go to the next level and ask what happens if the population sizes are correlated, which is more realistic. And because now I'm talking about correlation, so I have to go to the more specific model. Okay, so the model that I chose to work with is a simple model in which I just allow population size to take only 2 values, n1 and n2, and they interchange each other with the rate gamma. So this is your familiar telegraph process. So in this case, as you know, population sizes are correlated. Okay, so then we can write down Fokker-Planck equations, standard techniques. So this first term is due to the Wright-Fisher process, and the last 2 terms are due to the telegraph process. And these are of course coupled, and these are standard methods. One can solve it exactly, and you can look it up if you're interested. Okay, the key point is this: we have in this model just 2 time scales. Basically, if you look in from the dimensionally, n is the time scale, and 1 by gamma, that is the time at which switching occurs. Those are the 2 time scales in the system. So if switching occurs very slowly, that means population size remains almost constant in size, then of course that's one limit, okay, over here, which we know very well. Other limit is rapid switching, in which case population size is uncorrelated, because every generation it is choosing a new population size, right? Okay, so that case is also fine. There also we can define an effective population size. So the message in general, not just a specific model, is that when time scales are well separated, then it's useful to think in terms of effective parameters. But what happens then at intermediate time scales? Because nature is not going to tune things so that time scales are separated, right? So this model that I described to you, one can solve exactly as I said, but then these parameters are the same order. Then we find the results are substantially different, and I'll just give you the answers here. So I'm looking at, for example, probability of fixation as a function of time. The red line is the model that typically people consider. So the magenta is the one in which you get when the timescales are overlapping. So probability of fixation is substantially different, a factor of 2, which is huge. It is very large. There's another quantity which is of great interest to biologists. It's called mean sojourn time, which as physicists you know. Mean sojourn time can be related to genetic diversity, which is what these guys measure all the time, and they are sort of obsessed with how much is the diversity in the population. So this mean sojourn time can be related to diversity, and typically in the canonical cases, it decreases as a power law as 1 by frequency. Here I find that actually it does not decrease in the overlapping timescales. It does not decrease as a power law. It's something else. I know what something else is. I have a function for that. So the answer is pretty different. So therefore, if they were using these effective size theories, then they'll be incorrectly estimating the diversity. Okay, so that's the sort of the message for biologists. But what I mean to say is, the intermediate timescales, there are things that are of interest to them are substantially different, and that's basically the message, at least for them. Okay, so that's all I wanted to say, that effective parameters are often used in evolution theory, actually in general, in population biology, in ecology, etc. It's also pretty common because they're very complex processes. And the questions that I asked are answered here. These can be defined when timescales are overlapping. And this, at least in this case, is attributable to correlations, and the results are affected significantly. And the last line, I think all of you remember some RTP or active something here. So it's nice to be able to work in different fields and have some, use that model over there and so on. Okay, fine, I'll stop here. Thank you very much.
Thank you, ma'am. Question?
So this telegraphy process that you do, so you turn on after periodic times or random
No,
times?
no, it's just it switches with the rate gamma. So
Oh,
a typical time is 1 by gamma.
Yeah.
Yeah, it's a usual one that all of you do in RTP.
Yeah. Okay, thank you.
Yeah.
But then what is your suggestion in the sense that...
To them?
Yes.
Do a more detailed job, which means they can do only simulations. So, but I think it's in the subject, it's a conceptual problem because there are tons and tons of articles written about effective population size, and people just do that. So I think it's good to, if some simple-ish things one can demonstrate. So it's actually, for you guys, it's sort of trivial, but I think it's sort of important, I hope, for them. Yeah, but whatever, yeah. Okay.
Suppose this NT,
Huh.
made it switch between two states, but I guess more realistic assumption would be that it has some diffusion or some underlying dynamical process.
Yeah, so I modeled using telegraph process, but you can think of other stochastic processes, right? So therefore, you can come up with other ones, but depends on what you want. So you want to solve it exactly, or you want something which is useful for them. So there's something else that I'm looking at, which is a stochastic logistic equation. So N follows that process. That unfortunately is not doable, but it's relevant to them. But if you know of any examples which can be solved, I'll be very interested. Okay, thank you very much.
Thank you, ma'am.